Here we go. Module 2, Lesson 3, Horizontal Projectiles. So anytime something is shot to the right, so that can be an arrow, that could be a baseball, it does not matter. These ones just don't have any angle to them. Okay, so we're not worrying about some of the other forces that we will come back into play later. These ones are going horizontal. So if I'm going at horizontal at 10 meters per second at the start that the arrow was launched, then anytime that I check on that arrow in year 1 physics, that arrow is still going to be going 10 meters per second to the right or whatever direction it tells you until it's hit by a force. So when it hits the ground, that is when it would change its velocity. But we are assuming no air resistance. And that is normally what is going to stop you in the X direction. So without that, velocity average or velocity is constant. Okay, the velocity is not going to change for the whole part of the problem until it hits the ground. And that's a super nice thing to have there. So you'll have the horizontal projection and you won't have to break it down into its X and Y forces because this is all the velocity in the X, velocity in the X, unchanged or constant. So that's going to be helpful that way. What else do we know? We still are going to have that arrow would still fall back to Earth. That's why it eventually hits the ground. If there was no gravity, that arrow could just keep going, but it's going to fall down. So what's making it fall down? Acceleration due to gravity. Gravity is only going to affect the Y direction. So that gives us a nice little thing here. What was my velocity in the Y? It was 0. How do I know that? Because this guy was shot off completely horizontal. That means any vertical forces are not there to create a speed at the beginning. So that gives us a nice little clue. So that our altitude or our height or our distance in our Y can be used with a velocity of 0 and drops out some of those terms for helping you to solve things. So let's go hit some problems. Okay, when riding in a hot air balloon, the inexperienced rider starts dropping weights over the side. Assume air resistance is 0. How far away does the package land from where it was dropped if the balloon had a constant speed of 20 meters per second east and an altitude of 100? Draw a picture. Draw a picture. I cannot say it enough times. Okay, so, and I'm just going to draw a box. Okay, 20 meters per second east. That's my velocity where? Velocity in the X. Okay, what's my velocity in the Y? My velocity in the Y is 0. Why do I know that? The balloon is not talking about going up and down, at least not at this point. Okay, so there is no velocity in the Y. And it's holding steady at 100-meter altitude. Altitude is just another name for height, which is our distance in our Y. So lots of information right from just that first part. And do you want to get in the habit of writing, assume air resistance is 0? Yes, if you're going to end up going into physics or engineering, those are the things that you're going to have to say each and every time. So just get in the habit of putting it on your drawing. How far away does the package land from where it was dropped off? So the package is those little weights. And so if it's dropped over the side, and I don't care if you draw this picture with it going down like a staircase or going straight down, I just want to make sure you have it somewhere so that we can describe what's going on. What do we know? What did we talk about when air resistance is constant? That it does not change. But you're like, oh, but wait, these are the weights, not the balloon. But if I'm on the balloon carrying this package and I let go of the package, we were all going at 20 meters per second before I let go because he was part of the balloon. Okay? So think about it this way. If there was no gravity and we're going along at 20 meters per second and I let go of that weight would just keep going along with me at 20 meters per second because there's no air resistance. So that first package is at 20 meters per second. But what did we just say? It's constant because there's no air resistance. So even the package at the end, before it hits the ground, okay, it hasn't gone and hit the ground yet, still going 20 meters per second because there's no forces acting in the X direction because we don't have air resistance. Nobody's pushing any of these weights. Nobody pushed it down, nobody pushed it over. They just simply dropped it. Nothing else is affecting it. So my velocity in the X is actually going to be the average velocity of 20 meters per second. What else do we know? Okay, we know how tall it is. So let me think about this. What do I need to know to figure out what this distance is? So I want to know this distance, and that's also called the distance in the X or the range. Well, let me see. I have that velocity average equation, distance over time, a super simplified one, but since we have velocity average, I can plug it in there. So to find the distance, what would I need? I would need the time. Is there any way I can find the time? I can't find it from the X direction. What about the Y direction? What do I know? In the Y direction, I know the distance. I know the initial velocity, because remember, that's the starting velocity, because it's going, as it drops down, it's going to accelerate due to gravity. So I know I'm going to have a different velocity final in the Y. I don't know what that number is yet, but it's there, so I can draw it in the picture. Do I have equations that I can work with? Yes, I can look at those standard same three equations that I used in Module 1, same equations. So I'm just going to pull up one here to help you out. Okay, velocity in the Y is still 0. The acceleration is due to gravity. What do I know? The distance in the Y, that's the altitude, 100. Velocity initial in the Y, that's 0. So I don't have to worry about that first time value because 0 times time would still be 0. Okay, and then I have 1/2 AT squared, and I know that A is 9.80. Okay, what is letting me do this? If I drop a package straight down, okay, that means it had no starting velocity, or I shot it off and had it be a projectile velocity. It does not matter. With air resistance 0, it always comes back to air resistance 0. The time that this guy took, I'm going to call that time equals t, is identical to this guy's time. So they both hit the ground at the same time, even though one started with a horizontal velocity. So that's another proof that I can use this equation here. Okay, 100 is equal to 0 plus 1/2 times 9.8 t squared. Notice it's t squared, so make sure once you move all your terms around that you do take the square root. Okay, so if you have trouble doing that math part, come to a question and answer, and we can go through that math part so that you have it. Okay, but there it is, 4.52 seconds. So make sure that you are getting the same numbers that I did. And now we can go back and we can use this equation because we have the velocity average and we have the time. We just need the distance. This is the velocity average in the X. So that's our distance in our X. And that's where the chapter got the range formula. Distance in the X is equal to velocity initial in the X times time. So again, you can solve that problem that way and get your answer. So there it is there if you want to check and make sure that you are on the right process. Okay, when riding in a hot air balloon with 100 meter altitude, okay, so there's my picture, 100 meters. It's going 20 meters per second east. Okay, what question do we have this time? Assume air resistance is 0. Now we know the weights are dropped every 15 seconds. How far apart do they land? So I have my little picture again. Now I know I'm dropping them 15 seconds apart. So this is a totally separate problem. So don't use any of the information from the first one. Okay, they're being dropped 15 seconds apart. How far apart do they land? Well, how fast are each of these going? 20 meters per second. So each package is going to be 20 meters per second. Each package is going to be 20 meters per second going to the east. Each package is going to be dropped off 15 seconds apart. What do I know? Velocity average equals distance over time. I know how much distance the one package is going to move, which means I know how much distance the other package is going to move, which means I know how much distance the balloon is going to move. So if they are all moving at that constant 20 meters per second velocity, I just need to know what's the distance that 15 seconds has. So I know the velocity and I know the time, and I can insert that into the distance. Could I use the range formula in the other arrangement? Of course. Okay, dx is equal to the velocity in the x times the time. So anytime you're doing these, this is the general equation, but we can make it specialized for just talking about the x direction, and we can rearrange the terms into the range formula. Every time you can do that. Just remember, the x's have to go with the x's, so I can't put the altitude here for the distance because that is the distance in the y. And there you go. So you have that if you want to check that out later. Tiger Woods chips the ball at a perfectly horizontal angle, and it bounced along the fairway at 22 meters per second at a height of 10 centimeters. Perfectly horizontal angle. That means, again, that that ball is going 22 meters per second. Notice I still use a square. You'll see why in later modules, but feel free to use the circle for a golf ball. Okay, and it has a height of 10 centimeters. Height of 10 centimeters. Okay, what do I need to do? What is the question going to be on this one? Assume air resistance is 0. How far away is the first touch to the grass? Okay, so that ball is going to be pulled down by gravity, same as everything else. And what do we know? The time that it takes for it to land, because air resistance is 0, is the same as if I dropped a golf ball from the 10 centimeter height. Okay. The time here would be time t. I'm just using t as a variable to relate it, would be the same as the time for this section. Each time when I drop it or when I send it off with a velocity horizontal, the times are going to match because air resistance is 0. Notice this is in centimeters. So make sure you converted it to meters. The free fall time is equal to the projectile time. That's the official words for what I've just said right here. The free fall time, when there's only the force of gravity acting upon it, is equal to the projectile time. So if we know that, what formulas do we have? We have that distance formula again that we can use, okay? How far away is the first touch to the grass? So that's the range because that is the distance in the x, which is equal to the velocity in the x times the time. Same problem as before. We want to find the distance in the x. We have the velocity in the x. Remember, it's 22 meters per second. Doesn't matter where you're hitting it because there's no air resistance. It would be the same. So we need to find the time. What formula can we use to find the time? The dy formula, because that one is the altitude formula. So velocity initial in the y, it's hit horizontally. There is none. Acceleration is gravity, and my dy is 0.1 meters. So make sure when you're plugging those in that you're always using meters. Why? Because this is meters per second. You got to compare apples to apples. And then you still use that same formula, VT, but it's velocity in the x times the time, because range is what? Range is the distance in the x. And if you want to check your numbers out, 0.14 seconds for the time, which makes sense. It's going to be pretty short, okay, because we were only 10 centimeters off the ground, a tenth of a meter. And there would be our range, 3.14 meters before it hit the ground the first time. How long does it take for an object to be thrown up and then land? That's going back to those first projectiles. Thrown up and then land. It's really hard sometimes to find this time because that's the range time. Notice each time that we've done that, we've had that range, the distance in the x is equal to the velocity in the x times the time. Each time we didn't know what that time is. So how long does it take for an object to be thrown up and come back down? We were often not given the range. If you're given the range and the initial velocity, then yeah, that's how you can figure it out. But in these ones, we did not get that at all through this practice problems. So how else can I find the time? How else can I find the time? Okay. So if it was a projectile, we would know the free fall time is equal to the projectile time. Those are both the times. But this one is thrown up and then land. That means it has a velocity in the y. So this velocity in the y is not equal to 0 because something is being thrown up and down. Can I still use the altitude distance formula? I can, because what do I remember? At the top of this arch, my velocity final is equal to 0, because what goes up comes down. So we slow down until we get to a velocity of 0, and then we speed up till we get to the next part. What else do we know? That is the halfway point. That is the halfway point. So if we go V final equals V initial plus AT, and we know V final is 0, and V initial, they gave it to us, and we know our acceleration is due to gravity. What can we solve for? The time. That is the half the time. So if you have a problem where you have to go a little bit further, where they're actually throwing up the object or down, it's not a projectile in this manner. So if it's a projectile or it's free fall, you can just use the time directly. But if it's not a projectile where we had to actually launch it up, so it's not a velocity in the y is 0, then this is what you could use to find that time. Twice the time it takes for it to get to the velocity in the y direction of 0. So to get to that maximum height, half the time, then the fall back down the other half of the time. And we can calculate this first half, again, if air resistance is ignored. And have a great day.